모든 게 궁금해하실 때
Assalamualaikum and hi to everyone. My name is Muzhaffar. My matrix number is 202972. So today I would like to talk about a Taylor's polynomial and also Maclaurin. So firstly, from the definition of Taylor's polynomial, so let fx be a function such that f derivative of x exists for all x on an open interval containing a. Then for every x in the interval, there's some formula of the Taylor's formula, which is Taylor's. We can conclude that Taylor's is actually an expansion for the function that are differentiable. Alright, so for the history of Taylor's theorem, okay, actually Taylor's theorem came from the mean value theorem, which is the generalizing of the mean value theorem is the Taylor's theorem. So from the notes that I found, when we explore the generalization of the mean value theorem, which leads to the error estimates, this when the Taylor's theorem exists. So by Taylor's theorem, Taylor's can be used as expansion to do some approximation with error. So maybe when we do some approximation, there must be some error in the calculation. So by using this Taylor's theorem, we can calculate the error from the theorem itself. So that's for Taylor's theorem. However, I still need to talk about Maclaurin's polynomial. Actually, Maclaurin polynomials is one of the subtopic in the Taylor's, which is Taylor's can be positioned at any point. Some lectures note use C and some lectures note use A. So Taylor's can be positioned at any position in the curve. However, for Maclaurin's polynomials must be positioned at the center of the curve, which is when we equal the center, so the A or the C must equals to 0. Alright, so just now I just talked about Taylor's and Maclaurin. So basically, when we said that, as I mentioned before, Taylor's and Maclaurin actually kind of linked together. So the formula also almost the same, just different is, where is it? Yeah, the different only on here, which is at this you can see that this is the Taylor's formula, this is a general Taylor's formula. So the difference is the A. For Taylor's A, we can use any kind of points. However, for the Maclaurin's, the A will be 0. Alright, and also we can see with alright, so for this one, this is actually for Taylor's formula with remainder, which is, as I said before, this Taylor formula can be used for estimate the error in our expansion. So as you can see, the Taylor formula is plus with R and X, where R is the remainder, or we call it as the error of the expansion. So it's given that the error of the formula is equal to f n plus 1 c over n plus 1 factorial minus by x minus a. A is the point given with the power of n plus 1. Okay, that's all for this note. Okay, now we will move on to the comparison. Alright, so as for this one, as I mentioned before, so this is the Taylor and Maclaurin's. Okay, so for the summary that I make is, for Taylor's, in any function f that are differentiable, Taylor's theorem is an extension of a linear approximation to higher order polynomials. An explicit expression is used to get the error of the approximation. And for Maclaurin's is a theorem that actually in a Taylor series where the point C of the function is located at the center. So as I mentioned before, C or some lecture notes use A is equals to 0, and the comparison, okay, like I said before, right? According to the explanation, Maclaurin and Taylor seem like same to each other. However, the position of C or A is different. In Maclaurin, C of A is equals to 0 because it was positioned at the center, while Taylor can be anywhere in the closed interval. So that's for the theoretically for Taylor's and Maclaurin's, but maybe it's kind of confusing because too many words, too many theory, and maybe from the theory I try to find some example to show to you guys, so that maybe you guys can actually understand more better for the Taylor's and Maclaurin's theorem, and also with their reminder. Alright, just now I just talked about Taylor's and Maclaurin's theory from theoretically, but as for now, I'll try to try to find some example to make it all you guys more clear about these two theorem. And I found this question from internet. Okay, first of all, for this one actually is the general equation. This one is all general equation for the Taylor's polynomial and also for Maclaurin series. But for Maclaurin, we know that they are x or a or c is equals to 0. So which is mean this all a will all turn to 0. Okay, let's forget about that first. Now we move to Taylor's polynomial. Okay, from the equation asks us to find a Taylor's polynomial for fx equals to sine x at pi over 2. So now this pi over 2 actually is the a, right? So okay, now firstly to do this question, firstly we need to find the derivative. For this equation, right? For this equation, fx is equals to sine x. The first derivative, differentiate sine x, we will get cos x. The second derivative, we will get minus sine x. The third derivative, we will get minus cos x. And the fourth one, we will get the sine x again. Alright, this is the very first step you need to do. Okay, then the question said they want the Taylor's polynomial for the function at pi over 2. So now we need to get the pi over 2 first. Okay, now okay, so this is the second step. Okay, for f pi over 2, okay, we will get sine pi over 2. Sine pi over 2 is equals to 1. Okay, for second derivative, cos pi over 2, we will get 0. For third derivative, minus sine x, which is minus sine pi over 2, we'll get negative 1 for, actually this is first derivative, this is the second one, and now the third one. Minus cos x, x is pi over 2, equals to 0. And the fourth one, is sine pi over 2, so we'll get 1 again. Okay, now this is all the, actually this all is FA. Alright, this all is FA. As you can see, this is FA, F prime A, F prime A, and so on. And if you look at this one, actually this one, yeah, this one actually is not the expansion for this Taylor, but this one actually is the remainder of the expansion. So the equation, the expansion, we only came up until here only. This is Fn, which is the question didn't ask us for what, until what terms they want. So we will find, I'll try to take just until the fourth derivative. So after you get all this value, just put inside all this value into the general equation. Alright, so after you get all this value and you put into the general equation, this is the expansion that you will get, right? So this is S1, as this is the original. This one is the first derivative, which is we got 0. This one is the second derivative. This is the third, and this is the fourth one. And for this one actually is the general equation for this expansion. And for this one is the remainder, or we call it, we use it to calculate the error for this equation or the expansion, because as we know, to get the error, fx is equals to px minus rx. Right, so now we want the px right now, so like make px as a subject. So now we get fx plus rx. This is why we use the plus symbol for this one, because we need to add the rx. Okay, after we use it, okay, now as you can see, this one is times by 0, so anything that times by 0 will get the 0, right? So as you can see, for the second terms and the fourth term, it's actually 0, so we will don't see any 0 at our last expansion. So this is the last answer for this expansion. So if they want the Taylor polynomials, this is the Taylor polynomials that they want, right? This is the expansion, this is the first term, the third term, and the fifth term, and this is the remainder. Okay, as the question didn't ask us they until what term they want, so we just use the general form for this one. Alright, okay, how about for Maclaurin's? Let's use the same function as this one. Okay, alright, now as for Maclaurin, okay, we use the same function as before, which is the function is fx equals to sine x. Okay, for Maclaurin, as I mentioned before, for Maclaurin, the position is at the center, which is a equals to 0. So now a will equals to 0. Okay, so now we make the derivative, which is the first derivative for 0 is equals to cos 0, and we will get 1. Oh, before that,
the original one. F0 equals to sine 0 equals to 0. And the second derivative, we will get negative sign, and the function is 0, so we will get 0. And the third one, negative cos 0, we will get negative 1. And the last one is fourth. I take this function until fourth derivative only, okay? Which is sine 0, and we will get 0 again. Now we all have this formula, so what we need to do is we put all this formula into the general term as we do before. Alright, it's just similar to the Taylor's polynomial. Okay, after we put all this value into this general equation. Okay, I already wrote again the general equation. Okay, after we put it all the value into the general equation, so the expansion that we will get is like this. Alright, this is the original one, this is the first derivative, the second derivative, the third derivative, and the fourth derivative. And this is the general formula for this expansion. And also this one for the remainder. We also include the remainder one. The remainder one is because we want to add on the error that we get during the expansion, so that we might get the more accurate value for our result. Okay, so after we consider as this one, all the 0 one that we take, so this is the final answer for Maclaurin. Alright, this is the final answer for Maclaurin. So as you can see, we don't know until what term they want, so we leave it as n on at here, okay? But if the question already give until what term they want, so we can get more accurate answer for that. Okay, as we discussed about Taylor's and Maclaurin's and about the accuracy between them, so if we compare the mean value theorem and the Taylor's theorem, I think from my opinion, I think Taylor's theorem is more accurate if we want to find any answer, if we want to get more accurate value, because for the general formula itself that we discussed before, the Taylor's include the error of the approximation for the expansion that we make. However, for mean, there's no any error that includes in the calculation, so that's why I think that Taylor's is the better way, or the better methods for calculate or to get a better result and more accurate. Alright, so that's all from me. Thank you so much for watching this video, and until we meet again next time, thank you.
Like a sinner, it's so fire with him. I go boo. He said you look crazy, thank you, baby. I'll eat all to you. Got me all messed up. His love is my favorite, but you plus me sadly can be dangerous. Lucky me, lucky you. Can't go get 거짓말 we lie. So what? So what? 만약에 내가 널 지우게 된다면 so sorry. I'm not sorry. Now.